Flap gates are a fundamental part of hydraulic engineering and water management systems. They are designed to permit water flow in only one direction, typically from a controlled or enclosed area to an open or uncontrolled water body, such as a river, lake, or ocean, while preventing the reverse flow of water into the system. Their importance lies in their ability to offer a passive yet effective method of managing water levels, preventing flooding, and maintaining system integrity in a variety of applications, including drainage, sewage, stormwater control, irrigation, and flood management systems. The basic concept behind a flap gate is rooted in the principle of differential water pressure. When the water level or hydraulic pressure on one side of the gate, usually the upstream side, exceeds the pressure on the downstream side, the flap gate swings open, allowing water to discharge freely in the intended direction when the pressure equalizes, or when the downstream pressure becomes greater, such as during a high tide, storm surge, or river flood. The flap gate closes automatically, thereby preventing the backflow of water into the protected area. This automatic operation makes flap gates extremely valuable in situations where active monitoring or mechanical control is impractical or too costly. Structurally, a flap gate consists of a flat or slightly curved panel known as the flap that is hinged at the top, bottom, or side to a frame mounted on the outlet of a conduit pipe, culvert, or drainage channel. The frame must be robust enough to hold the gate in position and resist the hydraulic and structural forces applied to it during operation. The flap itself is often made from materials such as cast iron, stainless steel, aluminum, fiberglass, reinforced plastics, or rubber composites, depending on the specific requirements of the installation environment, including water chemistry, salinity, temperature, and mechanical load. In coastal environments, for example, flap gates must be constructed from materials that resist corrosion, and marine growth stainless steel or rubber composite gates are often preferred in these cases, whereas in inland or agricultural applications, lighter and more cost-effective materials, such as aluminum or polyethylene, may be used. The hinge mechanism is another critical component of the flap gate, as it determines how smoothly and reliably the gate opens and closes under varying flow conditions. Hinges must be resistant to wear and must continue to operate efficiently even after years of submersion in water and exposure to sediment, debris, and biological fouling. The performance of a flap gate is influenced by its size, shape, mounting orientation, and the waterhead difference across it. Larger gates require more force to open and are often equipped with buoyancy aids or counterweights to assist in lifting the flap under low flow conditions. Some flap gates include built-in seals or gaskets around the perimeter of the flap to ensure a tight seal when closed, thereby preventing leakage or seepage in critical applications such as flood control and pollution prevention. A reliable seal is essential. In urban stormwater management systems, flap gates play a crucial role by preventing tidal or riverine water from entering storm drains and flooding streets during heavy rainfall events or high tides. Many cities located near rivers or coastal areas install flap gates at the outfalls of their storm sewer systems. These gates open to allow stormwater to be discharged into the receiving water body, but automatically close if the water level rises outside the outfall. This simple mechanism protects urban infrastructure, homes, roads, and businesses from water damage and helps maintain the operability of sewer and drainage networks during adverse weather conditions. In agricultural settings, flap gates are used to manage irrigation water and drainage in fields and canals. They can help retain irrigation water in a field during watering periods and then allow for controlled drainage afterward in low-lying areas where land is susceptible to waterlogging or salinization. Flap gates can be used to regulate water levels in field drains and prevent backflow from main drainage channels or nearby rivers. This regulation supports crop health and soil productivity by maintaining optimal moisture conditions. Flap gates are also widely used in industrial facilities and wastewater treatment plants, where they help control the flow of treated or untreated effluent into receiving water bodies. They prevent the ingress of external water, which could disrupt treatment processes or cause overflows in containment structures. Similarly, in combined sewer overflow systems, flap gates are used to direct excess stormwater to overflow outlets during peak flow events, while preventing backflow of contaminated water into cleaner or upstream parts of the system. Flood control is one of the most significant applications of flap gates. They are commonly installed at the ends of culverts and sluices that pass through levees, dikes, or embankments, where their primary function is to allow the discharge of interior drainage water, while preventing floodwaters from entering protected areas during heavy rainfall, river flooding, or storm surges. These gates become essential components of integrated flood defense systems, particularly in low-elevation coastal zones or deltaic regions where the risk of inundation is high and the consequences of flooding are severe. In environmental protection and wetland management, flap gates are used to control water exchange between different zones, allowing for the maintenance of desired water levels, salinity gradients, or seasonal hydrological patterns. For instance, in estuarine ecosystems, flap gates can help prevent saltwater intrusion into freshwater marshes during dry seasons, while still permitting freshwater outflow during rainy periods in constructed wetlands designed for stormwater treatment or habitat restoration. Flap gates can be used to mimic natural hydrological rhythms that support biodiversity and ecological function. The advantages of flap gates extend beyond their functionality. Their simplicity and passive operation mean they require no electricity or complex control systems to function, reducing both upfront installation costs and long-term operational expenses. This makes them especially suitable for remote or unmanned locations where power supply and maintenance access are limited. Their robust construction and minimal number of moving parts also contribute to their long service life and reliability. When properly designed and maintained, flap gates can operate for decades with only periodic inspections and minor repairs. Despite their many advantages, flap gates also face certain challenges. Debris accumulation is one of the most common issues. Flap gates installed in areas with heavy sediment load, floating trash, aquatic vegetation, or ice may become blocked or stuck in the hinge area, preventing the gate from closing fully or swinging open properly. This can compromise the gate's effectiveness and allow undesired backflow or restrict the discharge of water. Regular inspection and cleaning are essential to mitigate this risk. In some designs, self-cleaning features or debris shields are incorporated to reduce maintenance needs. Another challenge is ensuring a proper seal under low-flow conditions, especially when the water pressure difference is minimal. In such cases, the flap may not close tightly and small leaks may occur. While this may be acceptable in certain drainage applications, it could be problematic in flood defense or pollution control systems, where even minor backflow must be prevented. To address this issue, some flap gates are equipped with enhanced sealing mechanisms, such as elastomeric gaskets, magnetic strips, or even inflatable seals that create a more secure closure under all flow conditions. Corrosion and material degradation can also affect flap gate performance, especially in environments with high salinity, acidity, or chemical pollutants. Material selection and protective coatings are critical to extending the life of the gate and ensuring reliable operation. Stainless steel and fiberglass reinforced materials are often used in aggressive environments where traditional metals might corrode too quickly. In addition, periodic maintenance, such as repainting, lubricating hinges, or replacing worn seals, is necessary to sustain performance over the years. Installation of flap gates requires careful planning and precise execution to ensure optimal operation. The mounting surface must be flat, stable, and strong enough to support the gate under all operating conditions. The alignment of the gate relative to the pipe or channel must be accurate to prevent binding or misalignment that could impair movement. In some cases, anchoring bolts or embedded frames are used to secure the gate to concrete headwalls or outlet structures. Additional design considerations include the anticipated range of water levels, flow velocities, and sediment loads, which influence the selection of gate type, size, and material. Modern advances in technology have introduced intelligent monitoring and control features to traditional flap gate systems. In high-value or high-risk installation, sensors can be integrated to monitor gate position, water levels, and flow rates. These sensors can transmit real-time data to a central monitoring station, enabling operators to detect blockages, failures, or unusual flow conditions immediately. Some systems even allow for remote operation or alerts that trigger maintenance actions before Problems escalate. This level of automation enhances the reliability and responsiveness of flap gate systems, especially in complex urban or industrial networks. In recent years, there has been growing interest in the use of environmentally friendly materials and sustainable design practices in flap gate manufacturing. Recycled plastics, low-energy production methods, and environmentally safe coatings are being explored to reduce the ecological footprint of gate production and installation. Additionally, engineers are considering the impacts of flap gates on aquatic life and are designing gates with fish-friendly features such as rounded edges, slow closing speeds, or alternative flow paths that allow for the safe passage of fish and other aquatic organisms. Flap gates can be compared with other hydraulic structures like sluice gates, check valves, and tide gates. Each has its own strengths and ideal use cases. Sluice gates offer fine control over water flow but require manual or automated operation and are more complex and expensive. Check valves are similar in function to flap gates, but are typically used in pressurized systems like water mains or pump stations rather than open channels. Tide gates, which are a larger and more advanced version of flap gates, are used in coastal defense systems and are often combined with pumping stations and levee networks. In terms of versatility, cost-effectiveness, and ease of use, flap gates hold a unique position within the broader category of flow control devices. Their passive nature means they can be deployed in thousands of locations without the need for constant human oversight. Their ability to withstand harsh environments and provide reliable unidirectional flow control makes them an essential component of both ancient and modern water management systems. From the canals of ancient civilizations to the sophisticated flood defense systems of contemporary coastal cities, flap gates have proven their enduring value across millennia. As climate change increases the frequency and severity of extreme weather events, including heavy rainfall, hurricanes, and rising sea levels, the importance of resilient and adaptive infrastructure like flap gates will only grow. Their role in protecting human settlements, preserving natural ecosystems, and ensuring the continued functionality of vital infrastructure becomes more critical with each passing year. Future innovations in materials design and system integration promise to make flap gates even more efficient, responsive, and sustainable, allowing them to meet the evolving needs of society and the environment. To conclude, flap gates are indispensable tools in the management of water systems. Their simple design and autonomous function belie their critical role in protecting property, managing resources, and safeguarding the environment. From the smallest drainage ditch to the largest flood control system, flap gates stand as silent sentinels, ensuring that water flows where it should and stays out of where it should not. Their continued development and intelligent application will help communities around the world adapt to the changing realities of water in the 21st century and beyond.